Today, in this video lecture, we will see derivation of torsional formula. So, this is circular shaft. Consider a shaft of radius capital R and length capital L is subjected to a torque T, capital T, on the free end and other end is fixed. See, this A end is fixed and other end torsion act capital T. Radius of this shaft is capital R and length is capital L. Write this. Consider a shaft radius R. Is subjected to a torque capital T on the free end and other end is fixed. Initially, the line of shaft is horizontal AB. See this A and B. Line of shaft AB is horizontal and this line of shaft AB is horizontal before twisting, and after twisting it takes position AB dash. See, AB dash. Before twisting, this line of shaft is AB. That means this. And after twisting, this line of shaft is this AB dash. That means line of shaft change before twisting and after twisting. After twisting, it takes position AB dash as shown. Now, shear strain angle BAB dash. See this angle BAB dash. Sorry, this BAB dash. There is disturbance due to Ganesh festival. Outside there is mic. BAB dash. Angle between BAB dash is phi. This is shear strain. This angle between BAB dash is shear strain. Right here. Shear strain angle BAB dash is equal to phi, and angle of twist angle of twist is this angle BOB dash. Between BOB dash is theta. This red color line is shear strain and this yellow color line is angle of twist. Angle of twist between angle BOB dash equal to theta. Let's give them as equation 1. Now for longitudinal section, see this A longitudinal section, tan phi is equal to opposite side upon adjacent side. Tan phi is equal to opposite side. Opposite side is this BB dash and adjacent side is this AB, and AB is L. So for longitudinal section, tan phi is equal to C. This is angle phi, opposite side BB dash upon adjacent side. Adjacent side is this AB. Therefore, tan phi is equal to BB dash upon AB is L. Length AB is capital L. Now from this equation, B dash is equal to tan phi multiplied by capital L. Now this angle is very small. Phi angle is very small. So tan phi is equal to phi. B dash is equal to phi L. Because angle phi is very small. Then give them equation 2. BB dash is equal to phi L is equation 2. Next is from cross section, length of arc. See, this is length of arc BB dash. Now, what is length of arc? Length of arc is equal to this radius multiplied by angle. That means we have to calculate length of arc BB dash, and length of arc is equal to this radius multiplied by this angle. So, from cross section, length of arc is equal to radius multiplied by angle. Length of arc is BB dash equal to radius is here C. This is small r. Small r multiplied by angle is theta. Angle of twist r theta. This is equation 3. From equation 1 and 2, we get, see, this BB dash is equal to R into theta, and this BB dash is equal to phi into L. And now from equation 1 and 2, we get phi L is equal to R theta. phi l is equal to r theta, and from this equation we get phi is equal to r theta divided by l. This is equation 4. Now, by definition of shear modulus is equal to shear stress upon shear strain. Shear modulus is denoted as capital G is equal to shear stress upon shear strain. Shear stress is tau and shear strain is phi. From this equation we get this phi is equal to this G, this right hand side, tau by G. This is equation 5. Now see this 4 equation and 5 equation. R theta upon L is equal to tau upon G, because phi is equal to R theta upon L in equation 4, and in equation 5 phi is equal to tau upon G. So equate equation 4 and 5. Tau by G is equal to R theta upon L. See, tau by G is equal to R theta upon L. In this R, this right, left hand side, therefore tau by R is equal to G theta upon L, and this is equation 6. Next, maximum shear stress occurs at radius capital R. See, this is small r, but see this small r is only this side, and up to extreme fiber, up to this side, this is capital R. So, for maximum shear stress occurs at radius R, consider this small r as capital R. So, maximum shear stress occurs at radius capital R. Therefore, tau by capital R is equal to G theta upon L. Consider this as equation 7. Now consider an elemental ring of area delta A and at a radius small r from center O. See, this is capital R. See, this dA is elemental ring of area dA. Now consider an elemental ring of area dA at radius r from center O, and the shear force on elemental ring is shear force is stress into area. Let me see step by step this route. Now consider an elemental ring of area dA, small dA at a radius small r. from center O. Shear force on elemental string is equal to stress into area. Shear force on elemental ring, consider this as dF is equal to stress into area. Stress as tau and area is small area dA. This small area dA. This H portion. And this tau is this, because we have considered small r. So tau is equal to g theta upon L into r from this equation 6. Now, next step is torsional movement on ring. Torsional movement on ring is small dt is equal to df into r. See here, we have to take moment at this point, and for taking moment at this point, this r get cancelled, this dA get cancelled, this df multiplied by perpendicular distance r. So, and torsional movement we notify it as small dt. df is this equation. We have to consider it equation 8. G theta upon L multiply by R multiply by dA and again multiply by R. This is dF multiplied by R. So dt is equal to G theta upon L multiplied by R square into dA. Now, torsional movement on whole section. We have to consider only for this ring section. For considering whole section, integrate this term. Now, integrating equation 9. This g theta upon L take common and integrate r square dA. And this r square dA we see in our previous video lecture. R square integration of r square dA is polar moment of inertia. And this is J. So equation, integration of small dt is capital T is equal to g theta upon L as it is, and multiply by integration of r square dA is this polar moment of inertia J. And this J take this left hand side, T upon J is equal to g theta upon L. So see, T upon J is equal to g theta upon L, and T tau upon R is equal to g theta upon L. Equate this equation 7 and equation 10. Okay. From equation 10 and 7, we get first C T upon J is equal to this g theta upon L is equal to T upon J is equal to g theta upon L is equal to g theta upon L is equal to tau upon R. So this is torsion equation. T upon J is equal to g theta upon L is equal to tau upon R. In our previous lecture, we see this torsion equation. This T is twisting moment, J is polar moment of inertia, G is shear modulus or modulus of rigidity, theta is angle of twist, L is length of shaft, tau is shear stress, and R is radius of shaft. So this is our derivation of torsional formula. First we calculate angle of twist, shear strain. Then with the help of simple geometry, we calculate this phi. Phi is this angle between B A B dash. We use shear modulus term in this derivation. Then we also use torsional moment on a ring, shear force on a elemental ring, and we get T upon J is equal to g theta upon L is equal to tau upon R, this torsional moment. Thank you very much.